In this video, we will continue our discussion of states of matter and phase changes by speaking about heating curves. The last video brought up the idea of phase diagrams, which shows when we change from one phase to another. Heating curves depict the energy required to change from one state to another and allows us to do calculations to figure out how much energy is required. Let's begin with a quick overview of what we'll cover in this video. We're going to start with a more detailed definition of what a heating curve actually is. And most of the time today we'll be spent talking about heating curve calculations. We'll break those calculations into two major categories. First, we'll discuss the amount of energy required to change the temperature of substance. And that's going to introduce some new information, like, for example, the concept of specific heat. And then we'll also talk about the energy needed to change the state of a substance, and we'll talk about something new to go along with this, something known as enthalpy, or in this case, enthalpies of change. All of these concepts come with an equation that's going to allow us to piece together a calculation that'll calculate the total amount of energy to do an entire heating process. Last but not least, once we understand the data associated with a heating curve, you should be able to construct your own heating curve based on the provided data. And that's going to be similar to the work we're going to do up here, but approaching the idea from a different perspective. This over here is an example of what a heating curve looks like, and this heating curve is actually pretty thoroughly labeled with what states of matter we're in, as well as what's happening in each of the phases. We'll go through all these concepts individually throughout the course of the video itself. And we'll get started on that right now. Now, most people think of temperature and heat as being the same exact thing, but they are actually two distinct concepts. Temperature, or heat I should say, is a form of energy, and it is measured in the units of joules. Typically this energy is associated with movement or kinetic energy. Temperature, on the other hand, is a measurement of the average speed or kinetic energy of a group of molecules in a particular sample. These two ideas are very clearly closely linked together, but as we'll see later on in the video, there are times when they do very, very different things. We need to make sure that we're clear about those distinctions. Back to our heating curve plot itself. When we plot a heating curve, we plot it again on a two-dimensional axis. The y-axis is where we plot our temperature data, and the x-axis is where we plot our heat data, or sometimes time. If our reaction is producing a constant amount of heat over a certain amount of time, that's a very reasonable measurement of heat as well. When we start looking at the details of a heating curve, we see that heating curves tend to have two very distinct parts that go along with them. There are sloped regions of a heating curve, and this is where the energy that's being provided is used to cause a change in temperature. We will also see that these graphs are going to contain specific flat regions. In these flat regions, the temperature is no longer changing because that same quantity of energy is now being used to change the state, to go from solid to liquid or liquid to gas. The fact that these two regions happen separate from one another tells us that energy can only do one of these two jobs at a time. We can't change temperature and change state at the same time. So this is a first example of a heating curve that we have, and we can see it's broken down into regions labeled by letters. And each one of these represents one of the different processes we talked about in the previous slide. First of all, we can see three sloped regions where we're getting a change in temperature. So change in temperature and a change in temperature. And likewise, we have two flat regions here where we're having a change in state. All heating curves are going to have this same general shape. The only thing that's going to change is the temperatures at which the two state changes occur, as well as the relative slopes of the lines. And we'll talk more about the details that go along with that a little later on in the video. We can, however, at this point in time, identify what's happening in each one of these pieces of the graph. For example, if we're below this state change, which is our state change associated with melting, this is our state change associated with boiling. If we are below the melting point, that must mean we're dealing with a solid. If we're above the melting point or below the boiling point, that must mean this state we're in here is the liquid state. And then past the boiling point, we must be dealing with substances or the gases. So again, From section A to B, we expect to see a temperature change where we're taking the solid and raising it up to the melting point. From B to C is when the substance melted, it changes state from solid to liquid. Once that melting has finished, we then start the process of heating the liquid from the melting point all the way up to the boiling point. Again, another change in temperature. Once you hit the boiling point, the temperature change stops, and the substance, all the energy that goes into the substance is used to cause the boiling, going from the liquid state to the gaseous state, and then finally from E to F, that's when we take our gas and heat it to whatever final temperature we're going to get to. Again, all heating curves work exactly the same way. The details, things like slopes, lengths of line, and temperatures, are what change from substance to substance. Now that we've identified the general shape of a heating curve, let's start identifying the specific regions in that curve and the calculations that go along with it. The first type of region we'll talk about is how to handle the calculations that go along with the sloped region. In these regions, heat is being used to cause a change in temperature. Since there is a unique use for the heat energy, we need an equation that relates that amount of heat energy to the total temperature change that occurs in your substance. We need a unique equation for the sloped regions. That equation looks like this. We have four variables we're dealing with in this scenario. The Q stands for the amount of heat energy in our reaction. The unit for this is typically going to be either the unit joules or the unit kilojoules. M is going to stand for our mass of the sample that we're actually changing the temperature of. This will always be in the unit of grams. And delta T is going to be our change in temperature. That's going to be in the units degrees Celsius, and it's always going to be whatever the final temperature is minus whatever the initial temperature is. You might have noticed we left off the C here. C is the new concept that goes along with this. This idea is known as specific heat. And what specific heat is going to be is a variable that basically links a certain quantity of temperature change to a certain quantity of heat. And it's a number that's unique for each individual substance. So let's dive a little deeper into the concept of specific heat. It has a formal definition. Specific heat is the amount of heat energy needed to raise the temperature of 1 gram of your substance up by 1 degrees Celsius. In short, specific heat is simply a mathematical relationship between the heat that you're providing and the temperature change that's going to happen as a result. Specific heat is constant for a particular substance at a particular state of matter, and specific heat is also a value that is commonly given to us. This table over here on the right shows a lot of specific heat values of a lot of different substances. One of these specific heats that we will be using on a very regular basis is this guy right here. The specific heat for water is 4.184 joules per gram degree Celsius. That means it takes 4 joules of energy to get 1 gram of water up 1 degree Celsius. When you compare that number to a lot of the other specific heat values on this table, we see that it is comparatively large. It's twice as big as any of the others. That means it takes at least 2 times the amount of energy to get liquid water to change temperature than, say, for example, it does to get ice to change temperature. It takes 4 times as much to get air than it does to take air to change temperature, and it gets pretty much 10 times as much to get iron than it does to get iron to change temperature. What this means is that it's very difficult to get the water temperature to change, and anyone who's ever boiled some water has seen this before, whereas the temperature of iron changes very, very easily. It takes 10 times less energy to make that temperature change occur. If you have an iron pot on a stove, the iron pot changes temperature very quickly. Within a minute, it'd be too hard to touch, whereas the water inside the pot would change temperature very slowly. And again, all of that is tied back to the concept of specific heat. Now we can move on to our second equation, or our second calculation that we'll be doing. This equation deals with when we're doing calculations for the flat regions on the chart. In the flat regions, our heat energy is being used to change state. Again, because it's a different use of the energy, we need a separate equation, and this equation needs to relate that quantity of energy to the amount of energy it takes to boil or melt a chemical per unit of chemical we have. That equation looks a little like this. Again, Q is going to be our heat energy data. That is going to be in the unit of joules again. N is going to be a number we talked about earlier in the year. Instead of keeping track of how much we have with grams, this is how many moles of chemical we're dealing with. And delta H is something new, known as our enthalpy of change. And just like before with specific heats, we'll talk a little bit more about what enthalpy of change actually is. So diving into enthalpy of change by definition is the amount of energy needed to convert a substance from one state of matter to another. Backing away from this definition a little bit, we can talk about the definition of enthalpy itself. And enthalpy is basically the sum of all the internal energies of a system. So you can imagine within a bottle of a chemical, there's a lot of different forms of energy in there that can all be added up. The sum of those energies is something we refer to as enthalpy. Now, unfortunately for us, enthalpy is impossible to measure this total. You'd have to keep track of all the energies within a system all the time, and that's just a number that's really difficult for us to get. Not so much difficult, but definitely impossible. We can, however, measure changes in enthalpy. When a chemical reaction gives off energy or absorbs energy, we can see those changes, and we think of those changes as in delta H, which is the symbol we refer to as when we talk about enthalpy. To hopefully explain this a little more clearly, we can look at a graph such as this one here. In this graph, we can see that we have a certain amount of reactants that have, say for example, some sort of fuel and oxygen, and they have some sort of value of enthalpy here. We don't really know what this enthalpy is, but we know it's a large amount of enthalpy. When this reaction happens, the end result is the products, carbon dioxide and water, have a different enthalpy value. Again, we don't know what it is, but we know that it's going to be a certain amount of less energy because we know when we burn fuel in the presence of oxygen, a whole lot of heat energy is given off in the process. And that heat energy that's given off can very easily be measured. Therefore, we can say that the difference in the amount of energy enthalpy from before and after the reaction, which we can measure in the form of heat given off, that's going to give us our enthalpy or our change in enthalpy throughout the entire process. So let's get back to the enthalpies of changes that we're specifically interested in. There are two of them that we need to know about. The first one is going to be the heat of fusion. Heat of fusion is the energy needed to cause a substance to melt. It is symbolized with this delta H FUS for fusion. The second one we need to be aware of is the heat of vaporization. Heat of vaporization is basically the energy needed to cause something to boil, to go from the liquid to the gas state. This is typically much larger than the heat of fusion, simply because gases are so much different than solids or liquids. The change that needs to happen to go from solid to liquid is relatively small compared to the change that needs to happen to go from liquid to gas. The symbol we use for heat of vaporization is delta H vap for vaporization. The units for both of these are going to be kilojoules per mole, and just like with specific heat, this is typically data that is going to be given to you. So again, let's take a look at our heating curve from earlier in the video, and instead of talking about what's happening in each section, let's start talking about the equations and how they associate with each phase of the graph. In these sloped regions, again, we said we'd be using the equation Q is equal to mc delta T. The specific heat C is different for the three different states, so in this case it'd be the specific heat for the solid. Here it would also be Q equals mc delta T, but this would be the specific heat of the liquid. And last but not least, this last slope region would be Q equals mc delta T again, but this would be the specific heat of the gas. I could calculate how much energy, for example, it takes to go from letter A to letter B simply by plugging in the mass of the sample I'm heating up, the specific heat of the solid, and then whatever the temperature change is, read from the graph, going from whatever B is to whatever my starting temperature was. Likewise, in the flat regions, we said the Q was going to be Q is equal to N times delta H. We said this region was melting, so we would use delta H of fusion, whereas up here we'd say Q is equal to N delta H again, but in this case it'd be delta H of vaporization. I could calculate the amount of energy it takes to boil my sample simply by knowing how many moles of my sample I have to boil and multiplying that by the delta H of vaporization. Last but not least, we can take these calculations further. Say, for example, I have a block of ice below the melting point. I can actually calculate how much energy it takes to take that block and bring it to the melting point, the energy it takes to melt it, and then finally the energy it takes to bring that block up to some desired temperature. This would require multiple steps of calculation, and I could do 3 separate steps. I could calculate the energy to go from A to B with my Q equals mc delta T equation, from B to C with Q equals N delta H, and finally from C to my final temperature with Q equals mc delta T again. The total of those 3 calculations would get me the total energy to go from the beginning to the end of my process. We'll definitely try a bunch of these in class to make sure that they make sense, but at the end of the day, it's really just plugging numbers into equations and adding up the results. All right, let's bring this video then to a close with the last concept I wanted to talk about, which is constructing a heating curve. You can build one of those curves that we've been seeing in this video simply by looking at the same data we've been seeing so far. So what we're going to be doing here is taking thermochemical data. All that data we've seen so far is exactly that. Things like boiling points, melting points, specific heats, and heats of change. Those are all of our thermochemical data. With that data, we can basically determine the slopes of the different lines, how steep they are, simply by looking at values of specific heats. Namely, a higher value for C means it takes more energy to change temperature, resulting in a flatter slope. Imagine you have it on a hot plate. It's going to take that hot plate a longer period of time to make the temperature of the water change if the specific heat is higher. Likewise, if it's lower, it takes less energy to change temperature, and we expect to see the slope be significantly steeper. The length of the flat regions then is determined by the heats of change data. If we have a higher delta H value, that means it takes more heat and energy to change state, which means it's going to take a longer time. The line on the graph is going to be longer. Lower heats of vaporization take less heat or time, lower heats of change take less heat or time, and as a result, the line will be typically significantly shorter. This is what a problem like this will eventually look like. You'll be given data like this on a chart, providing you with what all the melting boiling points are, all the different specific heats, and the heat of fusion and vaporization. And from this, we can actually construct the curve. First of all, we'll label on our graph where our melting point and our boiling point are going to be. The data tells us that the melting happens at 0 degrees Celsius for water and 100 degrees Celsius for the boiling. The first region we're going to do is that first slope region leading up to the boiling point. That's going to require the specific heat. That's going to require the specific heat of the solid. Looking at the specific heat of the solid compared to the others, it looks like it's comparatively small to the specific heat of the water. We said before that small specific heats are going to result in relatively steep lines. I would exaggerate the steepness of the line to make sure it's very clear. Once we reach the melting point, we would expect our substance to begin melting, requiring the delta H of fusion data in this case. That delta H of fusion is significantly smaller than the delta H of vaporization, so we would expect this horizontal segment on the graph to be relatively short. Once we get past that, we're going to start the process of heating up the liquid. This is going to require the specific heat of the water. This is twice as large as the specific heat of the solid or the gas, and as a result, we would expect to see a relatively flat slope for this, getting us all the way up to the boiling point. Notice this slope is significantly flatter than this. Once we do that, now the boiling process is going to start happening. This requires the heat of vaporization. This number is significantly larger, therefore we would expect this flat region to be significantly longer than the previous one. And then finally, last but not least, we would take the gas and change its temperature. Again, we have a specific heat similar to the specific heat of our solid. I would expect the slope of this region to be about as steep as the slope of the original region from before. We've now created a heating curve that is relatively accurate to the data that was provided for us about this particular substance. And as always, practice more of this in class to make sure that this makes more sense and that you have a chance to ask questions. So that's pretty much it for our video for today. We are expected to be able to describe what a heating curve is, and specifically identifying those regions on the graph. You should then also be able to calculate the amount of energy, again, for any region or potentially for multiple regions where you get the sum of many smaller calculations. Last but not least, you should be able to predict the relative shape of a heating curve based on, again, the same thermochemical data. We'll practice all of these skills in class to make sure that they make sense. Please make sure you write down some questions about what we saw in the video today, and we'll make sure that we address them when we sit down in class together.